Okay, in the last lecture we talked about the stability of linear systems, and we saw that a linear system is stable if all poles are in the left half plane. In this lecture the topic is how to figure it out if the poles are in the left half plane. So basically, as I said in the last lecture, when we say poles, we mean the poles of closed loop system, because the stability is basically defined for the closed loop system. First of all, I will give you an example of a closed loop system when we have a plant with the transfer function g of s and the controller. So let's say this is the plant, and we have the controller k of s controller, and for example we have the transfer function of the sensor, which we have shown with h of s. So we have sensor here. So when we say the poles of closed loop system, basically we mean that we should find the transfer function from reference to output, that usually we call it T of S. So T of S is the transfer function from R to U, which is shown by Ys over R of S. So as you know, this transfer function is actually the forward path. It is K of S, G of S divided by 1 plus K of S, G of S, multiply the feedback H of S. So if we multiply these functions out, and at the end we will have a fraction of two polynomials. If I show the polynomials, if I show the polynomial in the numerator with b of s and the polynomial in the denominator with delta of s, this is actually how usually we show the polynomial in the denominator. And this b of s and a delta of s, they are polynomials. And if we equate delta s to 0, if we set the denominator equal to 0, this equation, we call it characteristic equation. Characteristic equation. And the roots of this polynomial are the poles of the closed loop system. So this equation gives you the closed loop poles. Okay, let's see one example. We are going to see if this control loop is stable. So as you could see, we have a transfer function for the plant is 1 over s plus 1, and the controller is 5 multiply s plus 2 divided by s. Later we will see that this transfer function is a transfer function of a PI controller. So basically we have designed a PI controller for such a system. But in this chapter, we are only interested on the stability of the system. So as I said, we should form the closed loop transfer function T of S, which is basically K of S multiply G of S divided by 1 plus Kg if you multiply that out. So we have in the numerator we have Kg, which is 5 multiply s plus 2 divided by s multiply s plus 1. And in the denominator we have 1 plus the same fraction, 5 s plus 2 over s multiply s plus 1. And if you multiply that out, you will get 5 multiply s plus 2 in the numerator, because you do this common denominator here, and then you will cancel this denominator from here and here. So finally you will get s times s plus 1 plus 5 multiply s plus 2. So if you simplify that, you will get t of s is equal 5s plus 2 divided by s squared plus 6s plus 10. Because the characteristic, okay, let's see what the characteristic equation is. As I said, if you set the polynomial in the denominator equal to 0, which is s squared plus 6s plus 10 equals 0, this is the characteristic equation. In this particular case, because it is a second order system, it would be easy to solve it and find the closed loop poles. So if you do that, we get two poles, p1 and 2 is minus 3 plus minus j1, which means that the system has two poles at minus 3 plus minus j. Real, imaginary, and these are the poles. And because the poles are in the left side, of the imaginary axis, so the closed loop system is stable. So basically this controller that we have designed, it will stabilize the system. So the next question is, because this simple example we had here, because the system is second order, it's easy to find the poles of the characteristic equation. But what if the characteristic equation is of a higher order? So what should we do in that case? I will give you another example. In this example, suppose that we have a characteristic equation of order 4. So we have 5s to the power 4 plus 3s cubed plus 4s squared minus s plus 7 is equal to 0. And the question is whether or not the roots of this equation are in the left half plane. Before I tell you how we can solve this problem on paper, with pen and paper, I will show you how we can solve it using MATLAB. So easily you can type the function roots and then type the coefficients of the polynomial in a bracket like that. If you do that, basically this sign stands. Actually, I use this sign to show that it is typed on the command window of MATLAB. So if you do that, you will get these 4 poles. As you know, a polynomial of order 4, it has 4 roots. So we have 4 roots here, and as you could see, 2 of the poles are having negative real value, so minus 0.81 plus j 0.96 and minus j 0.96. So these 2 poles are in the left half plane, but the other 2 poles, because they have positive real value, it is plus 0.51 and the other one is also plus 0.51. So these 2 poles are in the right half plane. So if this polynomial is the denominator of a transfer function, so that transfer function is not stable. So it is easy to find the poles or the roots of a polynomial using a MATLAB command, but here I'm going to show you another method that actually you can use it and solve the problem by hand. But why I'm teaching that? Because in case of having a parametric polynomial, it can help. But other than that, because we have nowadays, we have access to many softwares, for example, MATLAB. So I will not I will not spend too much time talking about this method that I'm going to present, because as I said, always you have MATLAB to find the roots. So this method that I said that we can use it for finding the place of the poles, whether or not they are in the left half plane or right half plane, is called Roth-Horwitz criterion. And again, this criterion or this method doesn't tell you the exact place of the poles. It just tells you if there are some poles in the right half plane or not. And this is actually what we need for the stability. Stability doesn't depend on the exact place of the poles. What we need is just whether or not they are in the left half, all of them are in the left half plane. So this method, as I said, is called Roth-Horwitz criterion, and it is basically a method to find the number of roots of a polynomial in the left half plane, right half plane, and j omega axis. Let's see, I will tell you actually how to use this method, and to do that we can use this example, this fourth order example, which is basically a general example because the coefficients are parametric. So we have dentices a4s to power 4 plus a3s cubed plus a2s squared a1s plus a0 is equal to 0. It is fourth order polynomial that we are expecting to have 4 roots for that. So how to proceed? Basically, we should draw a table, and in this table, so like in the left side of the table, we sort or we write the power of s from the highest power to the lowest power. So we start with s to the power 4, because here we have s4. If we had s, for example, 6, we should have started from s to power 6. Anyway, s4, s3, s2, s1, and s0. When you do that, in front of s4, you have one row here, and basically you have different rows here, and the row in front of s4, you should write the coefficients of the polynomial starting with a4. But we don't write a3 here because we should write every other coefficient here. So when we have a4, the next one would be a2, and again we don't have a1 and we have a0. So every other coefficient. And in front of s cubed, what we have actually the coefficient of s cubed, which is a3, and again every other coefficient. So basically we have a3, a1, and here it would be 0. So basically in the first 2 rows we will have all coefficients of the polynomial. So the question is how to proceed, how to write the third row. If I name the elements of the third row with b1 and b2, and then the next row as c1, and the next one as d1. Okay, why I don't write b3 here and, for example, c2 here and d2 here is because this table, it's kind of a rectangle. So if you draw a rectangle here, actually the elements to the right of b2 is 0, and also this one would be 0. So you don't need to write that. We will see that later. Actually, even if you want to write it, it would be 0. So if I assume the parameters here, let's assume that we have a C2 here as well, and then I will show you that C2 is 0. So how to find B1? Actually, B1 is to find B1. It has a general form minus a determinant divided by the first element of the previous row. So we are talking about B1. It would be minus a determinant. I will talk about that determinant later. But it would be minus a determinant divided by the first element of the previous row. So it would be A3. It is also the same for B2. Again, it is minus a determinant divided by, again, the first element of previous row. So in the denominator, always we have the first element of the previous row. Okay? But okay, now let's talk about the determinant here. In this determinant, what we have, basically we have 4 elements because this is a determinant of a 2 by 2 matrix. So we are talking about 4 elements. The first row is always the first column of the 2 previous rows. So the first column, let's say we are talking about B1, so it's the first column here, it would be A4, A3, because you should go, other than this row, the 2 rows before that, you should pick the first column, which is A4, A3. It is the same also for B2, so it is A4, A3. So basically what you have here is the first column of the 2 previous rows. What about the next column here? So the next column here, it depends on what element you are talking about. The next column would be the next column with respect to that element in the previous 2 rows. So because if you're talking about B1, it would be next column, but in the 2 previous rows, it would be A2, A1. If you're talking about B2, it would be the next column. You're talking about B2, not the same column, the next column, but in the 2 previous rows. So it would be A0, 0. Okay, and what we saw here, we can actually practice that for C1, for example. What is C1? Because C1 is minus, again, a determinant divided by, so what is that determinant? Because we're talking about C1, it would be the first column in the 2 previous rows. It would be A3B1. And then the next column, A1, B2, and then divided, always it is divided by the first element of the previous row. Okay. What about C2? If you remember, I said that I will show you that C2 is 0, but let's see why it is 0. For C2, again here in the denominator we have B1, and the first column would be the first column in the 2 previous rows. It would be A3, B1. But here, what is the next column to C2? It would be 0, 0. Okay, if you have, if you form this determinant, it would be A3 multiply 0 minus 0 multiply B1, so it would be 0. And therefore C2 is 0. And let's see what we have for D1. For D1, we have, if we follow the same procedure, the denominator is C1, the denominator is C1 because we are talking about D1. The previous row first element is C1, and it would be minus B1 C1 B2. Okay, here it is C2, but we know that C2 is 0, so I will write 0 here. So the interesting thing here is that when you have the last element of this determinant equal to 0, what happens here is that actually you will get that one equal to B2. I can prove that because the determinant here is B1 multiplied by 0, which is 0 minus B2 multiplied C1, but there's also another minus here, so minus multiplied minus, it will be plus, and then B2 multiplied C1 divided by C1. C1 will be cancelled, so it would be B2. So if there is 1 0 here, then D1 is always the same element here. But anyway, you can actually calculate and show that it is the same element over there. So okay, now the table is completed, so I need to tell you how to use this table to find if there is any pole in the right half plane. After forming the table, so when you have the table ready, there are some steps that you should follow. After forming the table, the number of poles in the right half plane is equal to the number of sign changes in the first column of the table. Okay, I'll tell you what it means. When we have the table ready, what actually is important is only the first column and the sign of the elements in the first column. Before I give you an example for that, there is a remark regarding the table. Remember that always you can divide or multiply a row of the table by a positive number. I will show you actually this remark helps you to form the table easier in some cases because you have some big numbers and you can multiply by a positive value, because then you have smaller numbers and you can work with that easier compared to those big numbers. So always you can divide or multiply the whole row of a table by a positive value. Okay, let's see one example. The example I have here is a control loop, and the question is whether or not this control loop is stable. So what we have here, we have a transfer function 1000 divided by s plus 2, s plus 3, s plus 5, and there's a loop, there's a feedback actually around that. So the question is, what can we say about the closed loop system? Remember, here the open loop system, it has 3 poles, but having a stable open loop system or having a stable g of s, it doesn't mean that the closed loop system is also stable. Always you should actually you should check that. So let's before I form the table, I need to find the characteristic equation because we don't have the closed loop transfer function yet. So the closed loop transfer function t of s would be, if I name this one as g of s, it would be g of s divided by 1 plus g of s. So it would be 1000 divided by s plus 2 multiply s plus 3, s plus 5, and divided by 1 plus 1000 divided by s plus 2, 3, and 5. So if you simplify that, you will get it would be equal to 1000 divided by s plus 2, s plus 3, s plus 5, and then plus 1000. This is t of s. If you also multiply that one out, what you get, t of s is 1000 divided by s cubed plus 10s squared plus 31s plus 1030. So this is the closed transfer function. So it's clear that the characteristic equation is actually when you equate this denominator to 0. So we get the this okay, we had this transfer function. Now we have we can write the characteristic equation as it is shown here. Okay, to find whether or not this polynomial has any roots in the right half plane, we need to form the table, the Roth-Horwitz table. So the first row, as I said before, first of all, we have this s cubed, s squared, s1, and s0, because it is the polynomial starts from s cubed. We should have the same here. And the first row is every other coefficient, starting from the coefficient of s cubed is 131, and the next one is 101030, like that. Before we continue, we can continue like that, but before we do that, it would be easier if we actually divide the elements of this row by 10, because then we will have smaller numbers. So if we divide by 10, we will get 1 here and 103 here. Now it would be easier to work or to continue. So what is the element here? I can actually find it here. So it would be minus 131, 130. Why is it like that? Because when you have this element, you should write minus the determinant. And what is that determinant? Is the first column and the column after that element, which is basically this this determinant, and then divided by 1. Remember, we have divided the elements here by 10, so it's 1 and 103. So what do we get here is okay, because we have this minus, usually what I do, I calculate the determinant like reverse, because for the determinant we have the main diagonal, so multiplying the elements of the main diagonal, and then minus multiplying the elements of this secondary diagonal. So what I do it reverse, and then actually I remove this minus here. So 1 multiply 31 and minus 1 multiply 103, so it would be minus 72, because it's divided by 1, it would be anyway minus 72. So we have minus 72 here, and the element here is 0 because there is no next column here. What you get here, as I said, when you have a 0 here, that element comes here. You can actually write it, but it's not difficult to prove it. What we have here is 103. If you want to write it, you can of course do that. So it would be, if I want to prove that this one is 103, so it would be the determinant of, it would be the column on top of this element, the first column, it would be 10 minus 72, and then we have 103, 0 divided by minus 72. if you calculate that, you will see that it is actually 103. Okay. So this is the table, and what we should do, as I said, we should only look at the first column. I can highlight the first column, the sign of the element in the first column, by rewriting that. So we have s cubed, s squared, s1, s0, and the first element is plus 1. Just write the sign just to make sure that we are noticing what the sign is. And the next one is again plus 1, and the next one is minus 72, and the next one is plus 103. So let's see how many sign changes we have. So from plus to plus we don't have any sign change, but here from plus to minus there's one sign change. So there's one sign change here, and here from minus to plus there's another sign change. So we have two sign changes, two sign changes. Therefore, two poles in the right half plane. Therefore, the system is not stable. Therefore, the closed loop system is not stable. Remember, we are talking about this system. We had this system, the open loop was stable because the open loop has 3 poles. All of the poles are in the left half plane, but by having just a feedback around that, we formed the closed loop system. That was the closed loop transfer function. Then we work on the polynomial characteristic equation. We formed the table, and we saw that actually in the table we have 2 sign changes in the first column, and because of that, the polynomial has 2 roots in the right hand side, and the roots of the polynomial are the roots of this polynomial are the poles of the closed loop transfer function. So because of that, this control loop is not stable. So actually we decided about the stability, but because the polynomial, I can also mention that because the polynomial is of 3rd order, and we found that 2 poles are in the right half plane. So therefore we can say that the other pole, the last pole, is in the left half plane. But it doesn't help the stability because already we know that some of the poles are in the right half plane. But only if we are going to know how many poles are in the right and how many are in the left, because we found that 2 poles are in the right side, therefore the other pole is in the left side. Basically that was the Roth-Horwitz criterion, and that you can find the number of poles in the right hand side. But there is a special case. Actually there are 2 special cases. I will skip one of them, which is not that important, but the other one, because we are going to use it later when we design a controller, I will talk about that briefly. So there's a special case when a row is 0. I will show you why, by the way, this is a special case, and why it is important. You will see that in the next example. So as an example, suppose that we have a characteristic equation given as below. We have s to the power 5, 7s, 4, 6s cubed, 42s2, 8s plus 56 is equal to 0. If you want to form the table, basically you could as we talked before, we have a table starting from s to power 5, and then the power goes down all the way to 0. So s4, 3, 2, 1, 0. The first row, we have the coefficients of the polynomial starting from coefficient of s5 and every other coefficient. So it would be 1, and then the next one is 6, and then the next one is 8. For the next row, we are starting from s4, then we have 7, 42, 50, 56. Yes, this one should be 56. Okay, this is what we have for the first two rows. As I said, we can actually divide the these are the first two rows. As I said, you can divide the elements of a row by a number, and this is the case here because our elements can be divided by 7, so we will get 1 here, 6 here, and 8 here. And why is it as you could see, you have a row 1, 6, 8, and the next row now is the same, 1, 6, 8. So if you form the elements here, if you find the elements here, it would be 0, 0. It's not difficult to prove that because when you form the determinant, the two columns of the determinant are the same. For example, let's talk about the first element here. It would be 1, 6, and 1, 6 again, and then divided by 1, and we have minus here because you have two same columns here, so the determinant would be 0, so you will get 0. So it is 0, 0. Okay, so